All right, grade 11, good afternoon. So I'm hoping all grade 11s that are supposed to be here are here. And if not, like I said, after the session is done, I will be posting the live video session on my YouTube channel. And those that want to know where the YouTube channel, what the YouTube channel is, you can go to my bio, go and locate the link. The link is there on the YouTube channel. It's also, the YouTube channel's name is Maths is the Game, and you can take it from there. So last time we did exponential equations. We did the introduction of exponential equations, and we did the different types of exponential equations that have to do with numerical bases. And by numerical bases, we mean number bases. We categorized the types of numerical base type questions that we can get to 3 types. Obviously the basic ones, and by way of correction, let's just look at this. So for instance, this was our game challenge that we had received last time, that I had asked those who were in the live to actually do and complete. Question number 1, all right, where you have 2 to the power x plus 2 to the power x plus 1 is equal to 24, all right. And if you guys can remember very well, amongst the types of exponential equations that we can get the types where there's highest common factor, or where we have to take out a common factor. There's the type where there is difference of 2 squares, where we actually have to factorize using difference of 2 squares. And then 3, there is the trinomial type. And we looked at the types, the conditions that need to be in place in order for us to identify it being a highest common factor, a difference of 2 squares, or a trinomial. And then obviously there's the grade 8 to 9 type that you learned, where you actually have to isolate the base on either side, left and right, and you need to make sure that the bases are the same, actually getting the bases to a place where on either side they are the same, so that you can drop the base and equate the exponent. So those were your most basic problems that you did in grade 8 and 9. And then in grade 10 you started getting exposed to highest common factor type exponential equations, where the base is a number. You got exposed to dots type, and you got exposed to trinomial type. So for instance here, in these game challenge problems that I had asked for you learners to go ahead and do, all right, 2 to the power x plus 2 to the power x plus 1 is equal to 24, all right. If we look at the left hand side, we can see that for the prime base that we have, how many terms are there on the left? There are 2 terms. 2 to the power x plus 2 to the power x. So clearly the variable exponent, the coefficient for each variable are the same. So that would suggest that here we will be splitting the bases and taking out the highest common factor. So this is clearly a highest common factor type problem. Okay, all right. Then look at number 2. 3 to the power x plus 1, all right. 3 to the power x plus 1 minus 2 times 3 to the power x minus 1 equal to 21, all right. So again, this type of problem, the bases 3 to the power x plus 1 minus 2 times 3 to the power x minus 1 is equal to 21. Here you would also go ahead and split. You would split the bases again, and you take out the common factor. So in this case again, because the bases 3 to the power x with another term 3 to the power x, okay, I think let me do this. I think there are people that are just deliberately trying to distract the live for reasons that they know and I don't understand. Okay, so like I was saying, so for these terms, once again, we have 3 to the power x minus, so 3 to the power x plus 1, but for a different term, the base 3 to the power x, once again, the coefficient of the x is the same again. So this would also suggest that this is a highest common factor type problem. Okay. Here we have 9 to the power x is equal to 3. So here we can clearly see that this is a typical problem that we would have done in earlier grades, where we would change the bases to be the same, take out the common factor, and then solve. Okay. So this here, 9 to the power x is equal to 3. You can change 9 to a prime base, 3 to the power 2x, and then obviously drop the base and equate the exponents to solve for number 3. So this is basically a typical grade 8 and 9, but if you, it's a typical grade 8 and 9 problem that you would do for exponential equation. Then this one, 3 to the power 2x minus 4 times 3 to the power x plus 3 is equal to 0. So this problem here, you can see how many terms do we have? We have 1, 2, 3 terms. If you look at the base 3, look at the exponent, the coefficient of x. It's 2 here, whereas for this base, the coefficient of the variable exponent x is actually 1. So we can see here that the powers 1 is 2 times the other one, whereas if you take if you take 1, you multiply it by 2, you get this one. If you take this one, you divide by 2, you get the coefficient of this x exponent. So this is not a highest common factor type, it is a trinomial type. This is where you would typically then use either the k method, or you could factorize the trinomial so that you can solve for the unknown variable. Okay, and then once again look at number 5, 3 to the power 4x. How many terms? 1, 2, 3. But if you look at these two terms, 3 to the power 4x, the coefficient of the x variable is 4, whereas the coefficient of the same base is actually 2. So basically the coefficient of this one is 2 times the other one. So 2 times 2 would give you 4. If you divide 4 by 2, you get 2 back. So that means this is one of those problems which is a trinomial type. So typically, how would you solve this? You would use either the k method, or you would basically go ahead and factorize the trinomial. Now, for the benefit of those who may be like wanting me to do the corrections, I will not do the corrections in the live now. I'm just reviewing this so that we can just be reminded in our heads what it is that we learned last time. I will do a video where I actually factorize I solve these, and I'll post it onto the YouTube channel. Furthermore, I'll even post it on the group for those who are actually in the group, the WhatsApp group, and actually have these there as well. I'll also use the TikTok page and actually post the individual videos for each worked out problem so that people can follow what it is that I did for each individual problem. Okay, so that is just an intro, guys. Like I said, if you missed out on the previous lessons, you're more than welcome. Go to my bio, go to the link that is attached there. There's a link that is attached there that is actually called Maths is a Game 5 to 7. Click on it and then go to the YouTube channel. It's there. The video from the previous lesson is there, and you can check it out. Okay. All right. Now I need to slow down because we are going to look at variable type problems where we have to solve for an unknown for variable type bases, because we did numerical bases. So now we are going to change our attention to variable type problems, which means we are going to go into rational exponents. Okay. All right. So I'm sure you guys can see what I have on the screen there. I have x to the power m over n. So this here m over n is what we call a rational number. Okay. Why is it a rational number? Remember that a rational number is a number that has a numerator and a denominator. That is a rational number. A number that is basically having a numerator and a denominator, where the numerator is a integer and where the denominator is an integer. So this is basically a base x, which is a variable, and it's raised to the power m over n. All right, x raised to the power m over n. Thank you so much, Zuko Boss. Really appreciate the friendship necklace. So x to the power m over n. This is a rational number. Hence, we call it a rational exponent. It's equated to p. All right. So this is where, thank you so much, Precious, as well. I appreciate even the previous rows. I really appreciate that. So m, n, and p, okay, could be any real number. Any real number. M, n, and p. In other words, m could be any real number, n could be any real number, specifically integers in this case, and then p could be any real number. Okay, so this is where m, n, and p are actually numbers, but this is general. All right, so m over n is a rational number. What is a rational number? A number that can be written as a fraction, where the numerator and the denominator are both integers. Okay, so hopefully that makes a bit more sense. So if we take this rational exponent and if we want to solve for x, what we would do, according to what we've learned earlier on, is that we would take the reciprocal of the rational exponent, meaning we would actually multiply the left-hand side by the power n over m. In other words, m over n, the reciprocal or the inverse of m over n is n over m. So we multiply by that inverse or that reciprocal, n over m. But remember that what we do on the left, we need to typically then do on the right-hand side, which means we would raise the base p to the power n over m, which is the same reciprocal. What does this allow us to do? It allows us to cancel out the m and the m and the n and the n, so that we are left with what? We are left with x to the power 1, which is equal to p raised to the power n over m. So therefore, we know that our answer would be x is equal to p raised to the power n over m. So this is how we solve for our variable base x. Hence, I refer to these as when we have a variable base, the unknown. All right. Okay. So hopefully we can see this. I just want to run through it one more time. So what I said is we have x to the power, it's grade 11, rational exponents, rational equations. X to the power m over n is equal to p. How do we solve for x? We take the variable base x, raised to the power m over n, and we multiply the rational exponent by its reciprocal, n over m. It's like you are twisting the numerator for the denominator for the numerator, you multiply by that. And then what you do on the left, you must do where? On the right, which means p will also be raised to that reciprocal, n over m. Then what does that allow you to do? It allows you to actually cancel out the rational exponent. M over n times n over m gives you 1. Okay, and obviously x to the power 1 is just x, right? Okay, and then here look at the right hand side. Okay, then p is raised to the power n over m, which basically means that x is equal to p raised to the power n over m. So hopefully, guys, we can understand this, and this is very clear for us, and it makes perfect sense. So this is the most basic rational exponential equation you can get. The concept is locked into the fact that whenever we have a variable raised to a particular rational exponent, we always multiply by its reciprocal rational exponent so that we can get rid of the unknown in the numerator, or get rid of the rational exponent so that we can solve for the variable. Okay. Yeah, so I hope that makes sense. So let's look at an actual example. Example 1. Let's say we had x to the power 3 over 5 equal to 8. And the question says solve for x. Okay. So I'm hoping you guys are writing this down so that you can also like maybe do it on your own and actually check yourself out. I'm sure you guys can see that this is not as difficult or it's not as complicated as you think it is. It should be quite straightforward. X to the power 3 over 5. So first step, we multiply the rational exponent by its reciprocal so that the exponent we are left with is positive. Okay, positive 1 to be specific. So 3 over 5, the reciprocal is 5 over 3. But we know what we do on the left, we have to do where? On the right. Now our 8 raised to the power 5 over 3. Okay, so far so sweet. Then x is equal to, obviously what happens here, 3 over 5 times 5 over 3 becomes x to the power 1. Then on the right hand side, 8 can be written as the number 8 can be converted to the prime base 2 to the power 3. I hope you guys can see that. Very, very important. If you don't know how to convert 8 to its to its prime base, go to your calculator, you press 8, all right, there you can see 8, then you go to equal, all right, and then you just say shift allows you to select all your yellow appearing symbols for all the buttons that you have there. Then you go ahead and press fact. Then 8 becomes 2 to the power 3. So that's why we convert the 8 to its prime base factorized, which is 2 to the power 3. Then what do you see? What's 3 times 5 over 3? 3 times 5 over 3, surely you guys can see this, that 3 in the numerator will cancel with 3 in the denominator, in that 3 goes into 3 once because there's the highest common factor of 3, and 3 goes into 3 one time. So therefore our answer, 1 times 5 in the numerator is 5. Obviously there would be a 1 here, 3 over 1, 1 times 1 is equal to 1. The final answer is 5. So in other words, you have 2 to the power 5. Okay, and then that answer, as Uboidumelo has already indicated, x is equal to 32. Okay, so very straightforward, not a problem, very basic in that we are applying directly the concept that we've just learned, that we always, if there's an x variable isolated on the left, we always multiply the rational exponent by its reciprocal. But what we do on the left, we do on the right. Then if we do have a composite base, we change the composite base. Remember what a composite number is? It's a number that has more than 2 factors. So 8 has more than 2 factors. You convert that to your prime base, 2 to the power 3. If you don't know off by heart, you use your calculator. 8 is equal to shift fact. You get 2 to the power 3. Then obviously the reciprocal was 5 over 3 of 3 over 5. So you multiply 3 times 5 over 3. And sometimes, you know what, instead of going ahead and writing this out, you can always just go to your calculator and say 3 times 5 over 3. Your calculator will undoubtedly just give you the actual value that you're supposed to have as the exponent raised over 2. So there it is, 2 to the power 5. And then 2 to the power 5, you can use your calculator as well if you don't know it off by heart, and get 32. Okay, hopefully we are together so far. Can I move on to the next example? Right. Just gonna check out for consensus. Then I can move on. If people are saying good, okay, Gift says, yeah, we can move on. All right, let's look at another example, example 2. Okay, let's look at just a few examples just to get a variety of things and to notice certain things. X to the power 3 over 2 is equal to, so instead of having just a numerical value, that's 1, let's write a fraction. 125 over 8. Let's check this one out. What do we do here? So once again, the variable is isolated. It's raised to the power 3 over 2, which is a rational exponent. So how do we proceed? We take the reciprocal of the rational exponent 2 over 3 since the variable x is isolated. But what we do on the left, we must do on the sweet right. Then that leaves us with x is equal to 125 is in actual fact a what? Where is that what? Where is that 3 in the bracket? What 3 in the bracket? What are we talking about here? Amkela Mazula. Sorry, where is that 3 in the bracket? You are asking that question, so I don't understand. What do you mean? Which 3 in the bracket? Mazula. You typed something. Where is that 3 in the bracket? You've lost me. Okay, no comment. So 125 and 8. Can we write 125 is a prime base? Definitely. Okay, if we don't know, like I said, we go to the calculator. 125, we say equal to, we say what? We say shift, we say fact. And then what do you get? 125 is 5 to the power 3, as Musa said. So 5 to the power 3 over 8, already 8. We were able to write 8, remember, is 2 to the power 3. That's all raised to the power 2 over 3. Do you still remember that? Okay. Now, there is a very important derivation of a law that we should know by now, that if you have a to the power m, and let's say here you have b to the power n, and it's all raised to the power p, the relationship between these bases is one of division, a over b, raised to a to the power m, and b is raised to the power n. But they are all raised to the power p. So when you remove the bracket, what can you do? You can write this as a to the power m times p over b to the power n times p. So following this particular law of exponents, we can then apply that to this particular problem. So I repeat, a to the power m over b to the power n raised to the power p can be written as what? You simply distribute by multiplication the outside exponent to the respective exponents for each base. So this becomes a to the power m times p over b to the power n times p. So applying this, we can say 5 to the power 3 times 2 over 3 over 2 to the power 3 times 2 over 3. So finally, our answer here, okay, 3 times 2 over 3, you can simply use your calculator. It should be able to help you out there. 3 and the 3 cancel. We are left with 5 squared there at the top. Then in the denominator, the 3 and the 3, since the one is in the numerator and the other is in the denominator, leaves us with 2 to the power 2, which gives us the final answer of what? What's 5 to the power 2? 25. What's 2 to the power 2? It is 4. Okay, and we can leave that answer in that form as an improper fraction, all right? There's no problem in that. We wouldn't go to the extent of using the calculator and writing it as a decimal, because in this case we just want to purely be able to utilize the fraction if it's in fraction form. Or we can write it, I mean, if someone is going to ask me, can you write the answer as a mixed number? Yes, you can, all right? You wouldn't be wrong by doing that. But understand that if you leave it in this form, that's perfectly fine, all right? No marks will be omitted, okay? So you can leave it as 25 over 4. The improper fraction is a appropriate final answer, so you don't have to convert that into a mixed number. If you do, you won't lose a mark. If you leave it as 25 over 4, you won't lose a mark at all. So hopefully this is so clear for everyone that is on the live. So we looked at one problem where the numerical value was just a value, and then now we looked at where the right hand side had a fraction numerical value, okay? And I'm sure you can see that in both cases we've pretty much followed the standard procedure, just making sure that at certain steps we apply the relevant laws, okay? So hopefully that that is clear for people, and we can move right along. In fact, we will move right along. The next problem I want to look at, guys, okay, and if there are specific problems, you guys are more than welcome to actually contact me on the side after the session, but for now, there obviously is a designated plan that I have in place that I'm utilizing, but you are more than welcome to contact me on the side if you have any other specific scenario you'd like to look at. So 4x to the power, let's look at this one. 4x to the power 3 over 4, which is equal to a half, right? Okay, so this one, we are adding a little bit more to the problem, because remember, when we started out, we started off with a variable with a rational exponent with just a numerical value. Then we moved on to a second example where we had a variable with a rational exponent and a fraction. Now, what have we just done? We've put a coefficient to the variable x raised to the power 3 over 4 equal to a half, which is this example. So what do we do with this example? Could we go ahead and straight up take the reciprocal of 3 over 4? Okay, so we can't do that as of yet because the variable is not isolated. There is a coefficient, so that means there's a step that we need to take care of. And Gift has given us an idea as to what we need to do. Okay, thank you so much, Gift. Gift there has given us a clue. So what we need to do is we need to eliminate the coefficient that is greater than 1. Okay, it's better when it's 1. When it's 1, then we can use the reciprocal, but we can't do that yet. So what we need to do, we use the multiplicative inverse, and we divide both sides by what? By 4. So you divide 4 by 4, you divide a half by 4, right? So this is practically the division, 4 divided by 4. Okay, and obviously when we do that, we are left with x to the power 3 over 4. On the other side, what's a half divided by 4, all right, or a half over 4? A half divided by 4, you can utilize your calculator, will give you 1 over 8. Okay, 1 over 8. Now we are at that place where we can apply the reciprocal. Do you see? So basically here there was a bit of uncovering first that we needed to do so that we can get to the place that we are familiar with. Okay, we couldn't just go ahead in this problem and apply the reciprocal from the get-go. We couldn't do that, all right, because we had a disturbance of this coefficient of x, which is 4, which was standing in the way. So until we can eliminate that, then we can actually apply the reciprocal. So what did we do to eliminate the 4? 4 has a relationship of multiplication with x. So to get rid of it, we divide by the value of 4. But what you do on the left, we do where? On the right. So we get x to the power 3 over 4 now, which is equal to 1 over 8. Remember, there's a 1 here, okay? Whether we write it or we don't, that does not mean it's not there. It's present, ever present, okay? So let's go. Then now we can apply the reciprocal of the rational exponent. So x to the power 3 over 4, we apply the reciprocal 3 over 4. What we do on the left, we do where? On the right. Okay. Yeah, let's just be careful that when we apply the reciprocal, we don't make a mistake of applying 3 over 4 on the left. You know, sometimes it happens these things, okay? It happens these things, but we need to make sure we apply the reciprocal all the time, okay? See, Boitumelo is way ahead of the games already, like at the answer. So obviously that will lead to a cancellation. X is equal to, our 1 there is good. Our 8 will be 2 to the power 3. All right. Then what do? We apply that exponent. So 1 to the power 4 over 3, 2 to the power 3 times 4 over 3. And I'm sure you guys can see that 1 to the power 4 over 3, anything raised to the power, well, if we have the base 1, any number that the base 1 is raised to will give you an answer of what? Of 1. Over 2 to the power 3, obviously the 3 and the 3 cancel, we're left with 2 to the power 4. Final answer, as Boitumelo had already indicated, will give us 1 over 16. Alright, so do you see here, we just simply apply the rational exponent to both the numerator and the denominator. Convert the 8 to 2 to the power 3. Apply the exponent, numerator and the denominator by multiplication to the exponent. Then we get 1 to the power 4 over 3 gives us 1. 2 to the power 3 times 4 over 3. The 3 and the 3 cancel. We get left with 2 to the power 4, which is in the numerator. So it's 2 to the power 4. And then final answer, 1 over what's 2 to the power 4? It is 16. Right? Step by step, simple genius. Alright. So 1, just remember that 1 raised to anything will always, 1 raised to anything, doesn't matter what it is, will always give us 1. 1 raised to anything will always give us 1. Okay. Alright. I hope we are feeling satisfied. Right. Now there's something else that I want to kind of throw in the spanner here. It's something we need to take note of. They are what we refer to as special cases. Okay, two very important special cases that we need to be very much aware of. As long as we are aware of these special cases, then we should never go wrong. Okay, just in case they throw a spanner in the works, we need to be mindful of these two special cases. So I'm going to look at these special cases for us before I change my attention and go to something else. Thank you so much, Black Melanie. I really appreciate the ice cream. Yeah, the weather where I'm at is quite hot, so ice cream really cools, it soothes the soul, if you know what I mean. Thank you so much. Okay, special cases. Special case number 1. So special case number 1 has to do with, generally speaking, if we have x to the power m over n, and we say it's equal to p, generally speaking, and we know that p is a positive number. Yeah? P is a positive number, generally speaking. So I repeat, if we have x to the power m over n is equal to p, this is general, right? Okay, you could replace the m and the n and the p with any real number, but we are acknowledging that p in this case is a positive number. And what? And m is an even number. So take note. If p is a positive number, but m, what is m? M is the numerator value of our rational fraction. And m is an even number. All right? Okay, so let's look at a practical example so that we can see what we are talking about here. Right? Let's say, for instance, we had x to the power. All right, let me just make the conclusion first. So an even power of any number positive or negative is actually positive. An even power of any number, positive or negative, is positive. Okay, so we're going to look at an example of what we mean by this. Okay, so I'm going to repeat it again, that if we have x to the power m over n, which is equal to p, where p is a positive number and m is an even number, okay, m is an even number, an even power, all right, of any number positive or negative, is positive. Okay, so let's look at this so that you guys can appreciate what we mean by this. X to the power 2 is equal to, x to the power 2 is equal to, don't worry, I'm going to explain the concept back again, all right? It's just that I want to look at the example, and then I'm going to use the example to reiterate or explain what I've just mentioned above about this special case. So let's look at this. X to the power 2 is equal to, let's say for instance, x to the power 2 is equal to 4. Right? So for instance, what do you see here? This is x to the power 2, all right? X to the power 2, and this x to the power 2, the exponent is even. Do you see that? So x to the power 2 is an even number. All right, hopefully you guys can see that this x to the power 2 is an even number. And if you were to write this as a fraction, this is like saying 2 over 1. Are you with me? So the numerator is definitely even, just like they said, when m is even, but p is positive. So you can see that most here, p is positive. Are you with me? Yeah. So an even power of any number, positive or negative, is positive. Okay. So x squared is equal to 4. If we were to solve for x here, x squared is equal to 4. Okay. X squared is equal to 4. When we solve for x squared is equal to 4, if we were to solve for this, solve for x, right? What we need to note here is the following. We would say x squared is equal to, and then we would take the reciprocal of 2, which is 1 over 2. But we would say plus or minus 4, and then what we would do with that plus or minus 4, we'd actually go ahead and take the reciprocal half. Okay. Let me just approve this comment, because I can see some comments are not showing here, right? So even numerator, denominator is odd. So what we acknowledge is that positive 4, the value of x can either be positive or negative, because the base for this particular even power can either be a negative number or a positive number. Yeah, we're going there, right? Then when we apply the reciprocal, we get x is equal to plus minus. The 4 can be written as 2 to the power 2, of course. Okay. Then what happens? The 2 and the 2, they cancel, because this 2 is in the denominator, this one is in the numerator. Those 2 cancel, we get x is equal to plus minus. Obviously, that will give us plus minus what? 2. All right, are you with me? So here, x can be positive 2 or x can be negative 2. I hope you understand that in this place of x, I can substitute either a positive 2, which is one of my answers, or I can substitute a negative 2, because as it says, an even power of any number, of a number, whether positive or negative, will lead me to a positive answer. Are you with me? So the answer can either be positive 2 or negative 2, because positive 2 raised to the even power will give me a positive answer. Negative 2 raised to an even power will also give me a positive answer. Okay, so this goes back to the statement. X to the power m over n is equal to p, where p is a positive number. P is a positive number. and m is an even number. We know that an even power of a number, positive or negative, is positive. The even power of any number, whether it's positive or negative, will give me a positive answer. Obviously 2 squared is positive 4. Negative 2 in brackets, the whole thing squared, gives me positive answer. Okay, so for this particular problem, please take note, whenever the numerator value m is even and you have a value on the other side that is positive, it suggests that we will get 2 answers for x, one positive and one negative. I hope you guys understand that. You can either get one answer that is positive, x can be equal to 2, or x can be equal to negative 2. So that is why when we take the reciprocal, we actually include plus minus. Okay, we don't proceed as in other examples. I'm sure you guys can have seen that in other examples. Let's just quickly look at the one of the examples that we had done. What do you notice here? Look at the numerator. Look at the numerator value for the rational exponent. The 3 is odd. Is this even? No, it's not. It's odd. How many answers? Only 1. The numerator is odd. How many answers did we get? Only 1. The numerator of the rational exponent it's an odd number. How many answers did we get? Only 1. All of a sudden, when the numerator of the rational exponent is even and there's a positive number on the right, that suggests that we will get how many answers for x? 2 answers, 1 positive and 1 negative. So this is basically something you need to be very mindful of, because if you're not mindful of this, you could easily not take into consideration that there are 2 answers and just simply go with the fact that there's 1 answer, but in actual fact there's supposed to be 2 answers for the value of x. I hope that is so clear for all of us where this rational exponent is concerned, where the numerator of our rational exponent is even. We are supposed to then have 2 answers, 1 positive and the other one being negative, as long as the numerical value on the right is a positive value. Very, very important. Okay, all right. So I don't know again if people have questions about this particular example that we've just done. I'm waiting for you guys to ask your questions of clarity. Okay. Hence they are saying it's a special case. It's a special case because whenever the numerator of the rational exponent is even, then you can expect 2 answers as long as the p-value or the number on the right is positive, guys. As long as the answer is positive. Okay. Yes. Okay. All right, I'm gonna move on because I see people are, I guess if silence means everything is great, right? Yeah. All right, let's look at special case number 2 then, because that was special case number 1. Special case number 2 has to do with the following, and I'm going to write the statement: when x to the power m over n is equal to a, where, okay, let's just use p to be consistent. Okay, let's use p, where p is negative and neither, this is grade 11, m or p is even, there is no solution. Once again, let us repeat. When x to the power m over n is equal to p, where p is negative, so in other words, the p is negative, and neither M or P is even. Neither M, sorry, not M or P, where neither M or N, sorry, not M or P, where neither M or N is even, there is no solution. Where either, sorry, not neither, why did I say neither? Where either, I'm saying where neither, where either M or N is even, there is no solution. Okay, if I repeat it again. So when x to the power M over N, so when x to the power M over N is equal to P, where P is negative, so this time round the number on the right is negative, and either M or N is even, there is no solution. Okay, so let's look at the example so that we can cover both bases of what this thing means. So let's look at this. X to the power 2 over 3 is equal to minus 5. Start right there. What is this statement saying? When x to the power M over N is equal to P, where P is negative. Where is P? P is the number on the right. What do we see here? The number on the right is negative. Okay, so it's meeting the condition. And either M or N is even. Okay, let's look at the rational exponent. Remember, M or N. M or N. So 1, if 1 is even, can you see an even number? Where do you see the even number? Do you see it in the numerator or the denominator? Is 2 even, or is it 3 that is even? Even numbers. Okay, it's 2, right? So here we have the even number is here. Okay, you guys get it, right? Yeah. Because this thing is saying either M or it could be N that is even. Then what are they saying? There is no solution. In other words, if this equation fits the description of this special case, 1, the right-hand side number is negative, 2, one of the values of our rational exponent are even, then basically we say there is no solution. So we would basically then say here, therefore, x has no solution. You wouldn't even proceed and try and solve it, guys. You wouldn't even proceed and try to solve it. Why? Because the case is very clear that if in your rational exponent, either your numerator or the denominator is even, and there's a negative number on the right, then it's out. It's out. And maybe some of you may be like, okay, maybe why is that the case? Let's do this. Let's just do it. Let's just try. X to the power 2 over 3. What's the reciprocal? 3 over 2, right? Then what we do on the left, we do where? On the right. So what would we do here? We would write negative 5 raised to the power 3 over 2. Are we together? Are we feeling it? These two cancel, right? We are left with x is equal to. I want to show you something quickly, and I want you guys to just be mindful. In grade 8 and 9, you guys did non-real numbers. Do you guys remember what non-real numbers are? All right. So I just want you to take for a second, without using your calculator, just for a second here. A to the power m over n, you can actually express this as a root. Okay, a to the power m over n can be written as a to the power m, the nth root. A to the power m over n can be written as a to the power m with the nth root. The denominator stipulates the root. Okay, the root, it's the nth root. Okay, the numerator stipulates the exponent of the base, and then this here, the denominator stipulates the root, so it's the nth root. So just come here very quickly. Okay, this is a negative number. Negative what? Negative 5. You're welcome, Michael. You're welcome, Michael. This is negative 5. I see your comment there. Negative 5. Then if you were to convert the exponential to root form, this is it. This is it. The root 5, negative 5 to the power 3, the square root of negative 5 to the power 3. If you take the calculator and put this in, this is what? And I want us to be very clear about our definitions. This is not undefined. It is non-real. When you get your maths error in your calculator, and this is something I'm trying very hard to explain to the grade 9s and the grade 10s, as I am doing whole numbers and rational numbers with them. Any negative number underneath a even root, guys, is not undefined. It is non-real. Non-real. It's an imaginary number. Okay, non-real. Undefined is when you divide by 0. Maths error here means undefined. There's a difference. Okay, there's a difference. Okay, so here, the even root of any negative number is non-real. This basically means x has no solution. So that's why we insist that if you see this special case condition where there's a negative number, and guys, either the numerator or the denominator of the rational exponent is even, do not even waste your time and proceed. Okay. Okay. Are you with me? So that's why you can actually look at this question and be like, okay, let me not waste my time. Let's just jump right straight to what it is. X has no solution, because you will apply your maths. Apply the reciprocal, because you know how to apply the reciprocal. Then you get here and you punch it into your calculator, minus 5 to the power 3 to the 3 over 2, and it's like, boom. We can't move any further. Okay? All right. So I hope you guys appreciate what special case number 2 is saying. All right?